Hey, this is Neo, and then today we're going to be doing a tank drive odometry tutorial. It's going to be pretty fast paced, so if you find an area that you're stuck on, just feel free to pause the video. So now we're going to start doing the math for odometry, so I would recommend getting a piece of paper and a pencil out. As a preface, the odometry calculation we're about to do is also known as the circular arc method. So basically, we assume all the movements that the robot takes are done in an arc, and these movements are incredibly small. So this is happening every refresh rate, so it's happening hundreds of times per second. So the white represents our robot's initial position, and here it travels a path to get to its final position, and the orange path is the delta. So each of these points can be expressed as x, y, and theta. So how do we calculate this delta? So first we can just draw some lines. And basically we can assume that it revolves around a center point P. And we have our two constants, d right and d left. D right is just the difference, or the distance that the right side of the robot travels. D left is the distance that the left side of the robot travels. And track width is basically the midplane of the left wheel to the midplane of the right wheel. So the first variable we're going to introduce is d-center, and using basic geometry we can deduce that d-center is just d left plus d right divided by 2. Next variable is the r left, which is just the radius of d left with respect to point P. Doing a basic arc length calculation, we can just deduce that d left is equal to phi times r left. And the same goes for r right. So next variable we're going to find is track width. And basically this is just the distance from the middle of your left wheel to the middle of your right wheel on your actual robot. And we define this to be r right minus r left. So we can do a simple addition calculation by just adding r left to both sides of our previous equation. So we get r right is equal to track width plus r left. The next step we're going to do is a subtraction of our second and third equations from each other. And this is already shown as the equation on the very bottom. This bracket just shows the two equations I was talking about. The next step you're going to want to do is factor phi up on both sides, so you'll get the following equation. From this equation, you can substitute in track width for r left minus r right because we defined this previously. The next thing you can do is divide both sides by track width to isolate the value of phi. Jumping back to r center, we can deduce that r center is just the average between r left and r right. This is just basic line math. So the next thing we're going to do is find the coordinates of P, and using trig, we can deduce that P of x is equal to x minus r center times cosine theta, and we get P of y is equal to y minus r center times sine theta. So these are the coordinates of P, and using the coordinates of P, we can actually find our new position of where the robot actually is. So to calculate the new coordinates of x prime, we're just going to take our point and then find the radius of our center. And so theta is actually the angle underneath phi. So if you add those two together, you can get the angle that it travels, and then from there it's just trig, which derives cosine phi plus theta. You can apply this same principle to find the value of y prime. You just take r center, and all the other math is the same. It's just you're using sine this time because you're calculating an offset of y. And your theta prime will just be your original angle plus phi, which is how much you shifted. So this is the new position of your robot, and thanks for watching.